I want to respect everyone's kind of boundaries and you know, privacy. If you have a question that you don't feel comfortable asking to everyone, just go ahead and, send it to the chat or something like that. You can send it as a direct message. Other than that, um, I'll open the floor to any questions. And if nobody has any questions, what I'll do is I'll start playing around with like amino acid structures and, titration curves related to amino acid structures and kind of progress through there. So, floor is open.
I do have a question.
Mhm.
This isn't like related to the review itself. Will you also be grading the extra credit for exam 4? Or is that already been graded?
Thank you for asking. No, it has not.
Okay.
So those questions I just left as being worth 0 points.
Mm-hmm.
And so I will be throwing those, I will be going back in, looking if you got them right. And if you got them right, I'll add 3 points. Um, so yeah, that's how I will be doing that. I have not yet.
Okay,
I
I was just
apologize for the delay.
wondering. Thank you.
Absolutely. Okay. Well, I think if it's all right with everyone, I'm just going to go ahead and get started. And where I always like to start is I like to start with sugars. Um, and yeah, I'll start with sugars, and then we'll use sugars as a mechanism to talk about amino acids, and we'll talk about yeah, we'll go from there. So, starting very broadly, um, sugars are also known as carbohydrates. Sometimes you might know them, or you might see them referred to as or known as um, polyhydroxyl, and then either ketones or polyhydroxy ketones or polyhydroxy hydroxyl aldehydes. Um, when it comes to sugars, I think that the most important structures to think about are your hexoses. Hexoses have a total of 6 carbons. And there's an example of a hexose. When it comes to an aldehyde, that is a aldose. So an aldose is going to have a functional group of an aldehyde at carbon position number 1. And the convention that I always use is I draw my carbon number 1 at the top. So there it is. Now, if it is a polyhydroxy ketone, then it's going to have the same 6 carbon structure. And the carbonyl oxygen is going to be at the second carbon. Now, the nomenclature that you should probably be familiar with and comfortable with would be like an aldose or a ketose, and then a aldo hexose, for example. What I'm going to be drawing on the left would be an aldohexose, on the right will be a ketohexose. Now, the sugar that I always like to start out with is glucose, and what I'm always going to do with glucose is I'm going to draw it as the D-glucose. And the reason that I'm going to draw the D-glucose form is because of the fact that, well, it's your biologically relevant sugar. Now, as a biologically relevant sugar, as a D sugar on our penultimate or our second highest numbered carbon right here, because this is a 6 carbon molecule, we have our OH group on the right-hand side. So at carbon number 5, in a 6 carbon sugar, we've got the OH on the right. Carbon number 6, CH2OH. So if we look at all of the carbons where we have hydrogens and oxygens, only this one, only in this case, the way that I've drawn it so far is a chiral carbon. Now, as I populate the rest of these, carbons 2, for instance, 2, 3, and 4, those are also going to be chiral carbons. And whenever I draw glucose, I follow a pattern of right, left, right as a when it's in its linear form. And that right is in reference to my hydroxide groups. So I'm going to draw OH, OH, and then OH. So I'm going to go like that, and then I know that all that I need to do is fill in my hydrogens. Okay, so there is glucose, D-glucose. It has 4 chiral carbons whenever it's in its linear form. And then, is this? Another thing to think about with respect to these, or with respect to glucose here, is that these hydroxide groups, like this one, they don't really like freely twist around and make the exact same molecule, but instead, if I do this right here, that molecule right there is not glucose, but instead, this is the carbon 1, 2, 3, 4. This is the C4 epimer of glucose. Okay, so anytime you see a hydroxide group on the opposite side of that D sugar, it's going to be the epimer of a reference sugar. So I'm referencing glucose. This is the C4 epimer of glucose. Now, if I were to take this right here, oh, and put my hydroxide group on carbon number 2, that's a 2 there, on the left-hand side, that is no longer an epimer because an epimer is a term that is reserved for only one location or variation at only one location. So I wouldn't say, oh, this is the C2, C4 epimer because of the fact that an epimer is reserved for one position. Now, in the event that I were to take this hydroxide group on carbon number 5 and switch that over, what's important to recognize is that it is no longer. So what I'm drawing right here, I'm going to erase this. What I'm drawing right here, what I have presented right now, is an L sugar. And I know that it's an L sugar because my hydroxide group on my second highest numbered or second highest numbered carbon or my highest numbered chiral carbon is on the left-hand side. Now, so that variation at that position, you're making an epimer. Now, if I wanted to draw, if I were to then go ahead and take my hydroxide at carbon 3 and switch that around. Okay. Now, this is actually L-glucose because this is the non-superimposable mirror image of D-glucose. So one thing that I want, or that's important to remember, is that D-glucose and L-glucose, it's not rotation of one hydroxide group. Instead, you have to move everyone over. So D-glucose and L-glucose are not epimers of one another. Okay. Now, when it comes to, so I'm going to go ahead and draw, this is L-glucose, but now I'm going to draw D-glucose again. And if anyone has joined new and they have any questions, please don't hesitate to stop me, send me a message, whatever you want to do. Um, I'm just kind of leading this as an arc throughout the semester. So if there's something that you have a specific question about, go ahead, send me a message, speak up, whatever. Okay, so here is D-glucose because I've got my second highest numbered carbon as has my hydroxide group on the right-hand side. Now, what I'm going to do with this is I want to cyclize this. And I'm going to cyclize this as a D-gluco um, pyranose. Pyranose. This is kind of the most common form of glucose that you'll see. Now, the way that I always like to start out drawing it is with CH2OH. This is carbon number 6. Carbon number 6 is going to go to carbon number 5. And I will, let's see, I'm going to jump around with different colors, I guess, as best I can. So that's carbon number 5. So I'm going to draw that right there. Okay. Now, the next thing that I'm going to draw is my oxygen that is bound to carbon number 5. And that oxygen is a part of my ring. So that oxygen being a part of my ring, okay, well, that had to form a link or form a bond with my carbon at position number 1. So I'm going to go ahead and fill in the rest of my ring, my 6-membered ring, because it is a pyranose. So I've highlighted these two atoms because this oxygen on carbon number 5, that is my species that has lone pairs of electrons and therefore a partial negative charge that will then proceed to go towards this partial positive charge on that carbon number 1. Okay, so this oxygen on carbon number 5 becomes a part of the ring. Carbon number 1 now undergoes a little bit of a change. Rather than having a double bonded oxygen to it, it has an OH. I've drawn it pointing upwards, and I'll come back to that in just a second, but that's significant. So it has a hydroxide group. In addition to that, it still has a hydrogen. So I'm going to draw the hydrogen here. So I will draw this double bonded oxygen as that oxygen that is, switch my color, sorry. I'm going to go to green so that I can keep that a little bit more clear. And then this hydrogen right here is this hydrogen right here. Okay, now that is my new ring. The ring has 6 members, 5 of them are carbons, and the way that I kind of always draw these and draw a glucopyranose or a pyranose in general is my right, left, right pattern. I kind of translate that to, well, carbon number 2 is where I started. As long as I'm drawing a D sugar, a cyclic D sugar, that right-facing hydroxide group is going to be down with respect to my ring. Okay, so I'm drawing that right there. Then my carbon at position number 3, right here. Well, that is pointing up. Up is translated from left. So then if you're playing along and you're trying to figure this out, well, we're now at carbon number 4, which is this guy. So previously on carbon 2, I said hydroxide pointing down correlates with on the right-hand side of my structure. If it is on the left-hand side of my structure, that hydroxide is pointing upwards. And so this right here is going to be pointing down. Okay. Now, that's kind of the cyclization of a linear molecule to a cyclic molecule, or sorry, the cyclization of a linear sugar. That's what we just looked at there. Now, what's happened in the process? Well, one thing that's happened is carbon number 1, which I'm going to get orange and circle. This carbon number 1, that's this carbon right here. Now, this carbon in the linear form is bound to 3 different things. And by virtue of it being bound to 3 different things, well, it is bound to, sorry, it's bound to 3 different things. And as a result of that, those 3 different things are not enough for this to be a chiral carbon. So I'm going to say not chiral. Meanwhile, in our cyclic form, well, that carbon that I've got circled in orange is going to an oxygen. And that oxygen is singly bound to another carbon. So that's unique. It's going to another oxygen. That other oxygen is a part of a hydroxyl group. So it's an oxygen to hydrogen. So those two, despite being the same atoms, are kind of different groups. The third thing is a hydrogen. And then the fourth is a carbon chain. So this carbon now has four different things that it's bound to, and therefore it is a chiral carbon. So when we look at a linear form of glucose versus a cyclic form of glucose, our linear form of glucose has four chiral carbons, two, three, four, five, two, two, three, four, five. Okay, so it's got four chiral carbons. When we cyclize it, then we get to five chiral carbons. Carbon number one becomes chiral. Now that carbon number one, I'm going to go ahead and say it's newly chiral. And it's newly chiral. And the significance of that is this gives us the opportunity to, well, basically look at two different variations of a sugar. So I drew this as D-glucopyranose, and I stand by that. But one of the things that I did that was kind of a, yeah, I guess so, a choice, was I threw this OH group up. Okay. That OH group could be pointing upwards, or it can be pointing downwards. And the difference between those is, well, by this hydroxide group either being pointed up or down, this is what is known as, and this newly chiral carbon is going to be designated as alpha or beta. And these two, alpha and beta, are known as anomers of glucose. So in alpha, well, that's what I've drawn right here now. My hydroxide group was pointing downward. Beta, my hydroxide group, is pointing upwards. So that's the kind of cyclization of a molecule like glucose. Now, the significance of that, one, we get a new anomeric carbon. Or sorry, we get a new chiral carbon, which is our anomeric carbon. Then number two is that this is alpha or beta designated, or that's kind of the terminology that we used. Now, this interconversion between alpha and beta, this is also known as muto-rotation. And in order for that to happen, well, the ring has to open up and that hydroxide group has to rotate, and then the ring can close back down again. Mutarotation is what that's known as, the interconversion from alpha to beta. Now, after that, let's see, so there are some other details and important things to know about. When this group right here, this alcohol, reacts with this carbonyl carbon, it forms what is known as a hemiacetal. In addition to that, it's somewhat common to refer to this as a reducing end. So you can refer to a sugar as having a reducing end or a non-reducing end when you're talking about a monosaccharide, an individual sugar. But what's a little bit more common is to look at what's known as a polysaccharide. So now I'm going to draw a simple ring. It's drawn poorly, Joel. Switch colors, sorry. So here's our simple ring. And then what I'm going to do is I'm going to have that pointing downward, which means that I'm talking about an alpha linkage. So that alpha, so I'm just going to label this as alpha. Then on my next sugar, I'm gonna have something that looks like this. So I can get basically the exact same sugar, and then this pointing down as well. So this bond right here is known as an alpha glycosidic linkage or bond. Sometimes you'll also see, or you might see something like blank glycosidic linkage. Well, in that case, what you want to do is you want to just look for what's the atom there. Well, this is an oxygen. So this is an alpha O glycosidic linkage. A variation of that is sometimes you'll see an N glycosidic linkage, but here we've got an alpha O glycosidic linkage. Now, with respect to this sugar, or this, what's known as what I've got right here, well, it's got two rings making up what's known as a disaccharide. That disaccharide, two sugars, done. Okay, so this is an alpha O glycosidic linkage. Sometimes you might see um, a particular sugar referenced as the beta form, in which case we might be looking at, well, or what we're looking at is this right here. That carbon, this, in this case, both of our anomeric carbons are pointing in the alpha position. The beta form of this would look a little bit like this, where the free anomeric carbon is in the beta positioning. So it's pointing upward. It's still got an alpha O glycosidic linkage or an alpha glycosidic linkage, but this is the beta form of this sugar. Now, from there, what we can do is we can say, all right, well, what else can we say about this free anomeric carbon? One thing is that this is a free anomeric carbon. This is what's referred to as the reducing end. Now, it's common for a disaccharide to have a reducing end and then I'm going to point over here, an NR or a non-reducing end. Now, when we get to more complicated polysaccharides, and um, you might have something, and just for the number of strokes that I have to draw, I'm just going to draw a bunch of squares. Imagine that these squares are these individual rings like here. Okay. So when we have these squares, there's a couple of things that you can recognize about this. This alpha O glycosidic linkage can also be referred to as a 1,4 alpha O glycosidic linkage because it's carbon number 1 to carbon number 4. Now, let's imagine that this is a bunch of 1,4 glycosidic linkages. Okay, those are the ones that are connecting. Got it. Now, we've also got our reducing end, and then we've got our NR or our non-reducing end. Okay, so this is an example of a polysaccharide with one reducing end and one non-reducing end. Now, in a molecule like glycogen, you're going to have something like this. Glycogen, your major fuel source and fuel storage source in humans and mammals, you might have something like that looks like this. Okay, so this is referred to as a branch or a branch point. This linkage right here between, I'm going to label it A and B, that is what's known as a 1,6. Still a glycosidic linkage, but it's a 1,6 alpha glycosidic linkage. Now, when you look at a polysaccharide like this that has a single branch, you're going to have still one reducing end and then another non-reducing end. So when it comes to like a formula for glycogen, glycogen's going to have, let's imagine it's one reducing end and then, well, at least one non-reducing end. And so then we'll just say one plus number branches. I can give myself more space than that. One plus number of branches. So if it has 655 branch points, well, then there are 600 and 656 non-reducing ends. Okay. So those are, I think, the high points of sugars. Talked about cyclizing them, looked at the important functional groups, the reducing end, the non-reducing ends. L and D sugars, those always have a tendency to trip people up just because there's a tendency from my vantage point of people who they say, oh, well, I just need to rotate this hydroxide group. My hydroxide group on my penultimate or my highest numbered chiral carbon, I just need to flip that. And it's not quite that simple because if you flip one, you've got to do all of them in order to draw the L variation of whatever sugar you're talking about. If you just want to draw an L sugar, or if you just want to, if your question is which of the following is an L sugar, then you just look at the highest numbered chiral carbon or the second highest numbered carbon. You look at that and you say, oh, well, my hydroxide group's on the left-hand side. It doesn't matter where anything else is. But, pay attention to the question. If it asks you which of the following is L, um, an L ketohexose, okay? Well, then you've got a couple of things. L sugar. So you're looking at carbon, in this case, a hexose, you're looking at carbon 5. Keto. Okay, well then I've got to have that ketone functional group. So carbon number 2 has to have my carbonyl oxygen. So those are just some of the important things to think about with respect to sugars. Now I'm going to go ahead and jump on to amino acids and proteins. And again, any questions, feel free to drop them in the chat or unmute yourself and say whatever you got. Amino acids and proteins. When it comes to amino acids, there are a couple of different organizations and groups of amino acids. There are your polar amino acids, and then there's your nonpolar amino acids. Now, within your polar amino acids, there are polar positive. There are polar negative, and there are polar uncharged. There's a tendency, I know from my own experience, whenever I took this class, I was like, okay, cool, there's polar, or there's positive, negative, uncharged. And each one of those falls into the polar or nonpolar. Now, that's something that I would later look back on and be like, that doesn't make any sense. Because if something is polar, or sorry, if something is positive, it is therefore polar. And if something is, oh, sorry, just a second. Okay. Um, these are if something has a positive charge, by virtue of it having a positive charge, it is polar. So therefore, it cannot be nonpolar. So therefore, there is no nonpolar positive, nonpolar negative, nonpolar uncharged. Well, there is a nonpolar uncharged because everything that is nonpolar has no charge, no effective charge. Now, these are your major groups. One other grouping is your aromatic amino acids. Now, the aromatic amino acids, those are your amino acids with rings. And those have a tendency to sometimes be categorized by themselves, but they can also fall into the groups of polar and non-polar. So those are your kind of most important groupings. Now, I am sorry, I'm going to come back to this in just a moment. I got a direct message that I'm going to address right now. The question says, one thing that I was curious about was when a deoxyribonucleotide that is phosphorylated at the 3' end. Okay. So this question was about, I think this is referencing a question on one of my exams. Um, D P A C G T P. Let me just make sure which. I think that this question is referencing something I need to go back and make sure that I have it keyed correctly. Um, so this is res and I will, okay, so to the specific question, I will look into this one. So I'm making a note to myself, check back. See,
It was number 18, Dr. Gray.
got it.
On
Thank you.
CHEM.
I appreciate that. I will look back at that and um, I'll just go through this example and then I will look back at that question before the end of the weekend. So thank you very much. Um, so this notation right here, when you see this lowercase d here, this is in reference to a deoxyribonucleotide. And then the other components of it, we see lowercase p followed by ACGT lowercase p. These lowercase p's indicate phosphorylation. And this is phosphorylated in two positions. This is phosphorylated at the 5' and 3' end. And so based on what the message was that I get, okay, I have to look at that question. I'm not gonna commit to anything on that right now, but I'm gonna look at that one. So anytime you see this lowercase p, that indicates that it's phosphorylated on the 5' end and the 3' end of a sugar, which or of a DNA molecule or an RNA molecule. Now, this right here is different from PACCTG. Well, this is only phosphorylated on the 5' end. This right here, ACCTG, lowercase p, is phosphorylated on the 3' end only. So that lowercase p indicates that there's phosphate in a specific location. Now, if you were to see something like this, ACCTG, well, it's not phosphorylated on the 5' or 3' ends of that molecule. However, one thing to keep in mind is what type of bond is connecting each one of the sugars of a DNA or RNA molecule. And that is a phosphodiester bond. And so one of the questions that I've historically asked is how many phosphorus are in this molecule? Well, there's going to be one here, one there, there, and there. So there are a total of 4 phosphorus because they are found between each one of the sugars. Now, what I was intending to mention but failed to mention was all of these molecules, and actually, I'm going to make one minor change to them so that I can kind of get away with this answer, get away with this question. There we go. All three of these molecules right here, yes, if it has a P, yes. So sorry, here we've got one phosphorus, one phosphorus. So this would be three phosphorus total. Same with this one, because there's a phosphorus here, here, and then there's the third. And this one, three phos total. Um, all of these three molecules that I have highlighted at the bottom, these are all RNA molecules. And you know that they're RNA molecules because of the fact that this lowercase d is not present. With that not being present, well, then you know that the sugar that's present is not a deoxy sugar, but instead a, not a deoxyribose, but rather a ribose. Okay. Um, Thank you very much for the question, and I'm going to take care of that. Okay, cool. I know you were going to technically this. Okay, thank you for that. I will take care of that. Um, okay, so now what I'm going to do is I'm going to go back to amino acids. So we've got our major groupings of our amino acids: polar positive, polar negative, polar uncharged, and non-polar, and then of course your aromatics. When it comes to amino acid structures, some of the important things to know, one, or sorry, before I get to amino acid structures, one thing important to know is the woman who's responsible for our one letter and three letter codes. Margaret Oakley, Oakley Dayhoff, bioinformaticist back in the 1950s, 50s and 60s. And she said there's got to be a better way to look at an or to look at a protein sequence than writing every single amino acid. Um, and so she devised a method or a mechanism that kind of simplified it, and that ultimately gave way to three-letter and one-letter codes. Now, typically, the three-letter code is the first three letters of the amino acid name, and the one-letter code is the first letter of the amino acid. There are some outliers to that. And the outliers are, so if not, first three letters or first letter. If it's not that, then what you're looking at is it's going to be something like a phonetic pronunciation. Or if it's not phonetics, then it's going to be kind of a pattern in the alphabet. So, for example, um, if you look at aspartic acid, aspartic acid is a negatively charged amino acid. It's a polar negative residue. Aspartic acid has the single letter code of D, and that would be a phonetic pronunciation. The amino acid glutamic acid, as a result of aspartic acid getting capital D as the single letter code, glutamic acid got E, because that's the structurally those two molecules are very similar to one another, and it was just the natural progression. Aspartic acid has a R group that looks like this, and it is a carboxylic acid, whereas glutamic acid looks a little bit like this. Now, there's no significance to how I drew my carboxylic acids or my carboxyl groups there. The double bond placement does not matter. It's resonance stabilized. Okay, so that's where those things come from. When it comes to if you're doing like a quick review of your amino acid structures and you're like, I gotta know these, um, what I think is most effective is to simplify this down as much as possible. We've got 20 proteinogenic amino acids. There's also two others that are a little bit less relevant to like human health. That would be your uh, pyrrole lysine and selenocysteine. In my class, I didn't even really, I think I mentioned them, but didn't emphasize them. So they're not huge deal. They're relevant to like some microorganisms. Now, when it comes to tackling these 20 proteinogenic amino acids, you're basically breaking it down into roughly 10 polar and 10 non-polar residues. And then the aromatics, you can break those down even further. The way that I like to approach it is I tackle my two negatively charged residues, then I tackle my three positive polar residues, and then I've got basically five, maybe six polar uncharged residues. And then the rest are non-polar. I think that that's an effective way to do it because of the fact that these non-polar residues, for the most part, they're just hydrocarbons. They're not all hydrocarbons, but many of them are. And as a result of that, they don't have a lot of, or they're not a big deal from a types of interactions that they can mediate. Because your non-polar residues, more than likely, they're just going to be involved in hydrophobic interactions. So those hydrophobic interactions, yeah, that's basically what they're going to do. Um, Whereas your polar residues, those are a lot more interesting because of the fact that they can be protonated and deprotonated. I know in my class, I'm going to provide my students with the pKa values, the necessary pKa values. That's going to be important for calculating things like a PI or looking at what the most or the most common or the predominant form of an amino acid at a specific pH. So, with that in mind, what I'm going to do, I think what I'm going to do is just, I'm jumping ahead quite a bit here, but I'm going to jump ahead to just because I want to give this adequate time. I want to talk about enzyme kinetics. When it comes to enzyme kinetics, there's a couple of things that are very important to know. And I'm sorry, this is, yes, I fast forwarded and I skipped over like 2 months of the class, but here we are. Enzyme kinetics, some of the important things to know about an enzyme are its Vmax. So how fast can that enzyme catalyze a reaction? Top speed, essentially. And the units for this, um, the units for a velocity are typically going to be something like micromolar or micromole per minute, or maybe something like this, nanomolar per second. Enzymes all vary in that regard. Another important kinetic parameter to understand is a Km. Now, Km is the affinity that an enzyme has enzyme has for its substrate. Now, another thing that's important to know about is Kcat. Now, Kcat is the measure of amount of substrate converted to product in a time interval. So I'm just going to say in a time. Now, the Kcat is valuable because what we can do is we can, and so our Kcat would be let's say that you have, I'm going to give you two different example enzymes. Ends A and ends B. Okay, so enzyme A. What enzyme A is going to do is it is going to take, 10 substrates and make, let's say, 10 products in 1 minute. Okay. Now, enzyme B, what it's going to do is it's going to take 10 substrates and make 6 products in 1 minute. Now, what we have to take into consideration with respect to enzyme A and enzyme B is looking at their overall structure. If we say that enzyme A, if we learn that enzyme A is, let's say that it's 10, it's 10 polypeptides, and each one of those polypeptides has its own active site. That's 10 active sites. And so when we do this, our kcat is also a measure of per unit or per enzyme unit, I'll say. So we have 10 active sites. So effectively what we would do is we'd say 10 substrates into 10 products in 1 minute, but we got to account for those 10 active sites. So we're going to say 10 divided by 10. So we're going to have a kcat for this enzyme of 1. Enzyme B. Well, enzyme B, you learn a little bit more about the structure and you learn that it only has one active site. So what we're kind of comparing when we look at kcats is how effective, I'm going to get to that one next. How effective is each active site? That's what, so I'm going to rephrase this. Kcat is active site, I'll say productivity, efficiency. Yeah, I'll say efficiency. How efficient is an individual active site? So we would say 10, and we're making 6. So actually, I'm going to, sorry, get rid of that. I'm going to say 6 products were created with one active site. So we're looking at a kcat of 6. Okay, so if we're comparing enzyme A and enzyme B, and we're comparing the active site efficiency, productivity, well, arguably enzyme B is better based on that. Okay. Now, what we that's one other valuable component of this. So enzyme A has a kcat of 6, enzyme B has a, or sorry, enzyme A has a kcat of 1, enzyme B has a kcat of 6. Now to compare those even further, so we can look at our enzymes, and actually I'm going to change, I'm not going to say efficiency. I'm going to say productivity. An enzyme's efficiency. An enzyme's efficiency is measured by looking at your kcat divided by your km. Okay, so I'm going to erase all of this, the calculation that we just did, and I'm just going to define enzyme A as having a kcat of 1 and enzyme B as having a kcat of 6. So kcat 1, kcat 6. Okay, so now what we want to do is we want to compare these two enzymes and say which one of them can basically, get its substrate very easily and convert it into a product. We have our K-cat, but we have no idea of how much each one of these enzymes wants to get its substrate. On the surface, we'll look at these K-cats and say, oh, enzyme B is better because it can get the substrate, or sorry, it can convert the substrate into the product. The active sites of enzyme B are better. Enzyme A, in order to be that productive, it's got to have 10 copies of the enzyme. Now, what we're going to do with this is we're going to look at the affinity that each one of these enzymes has for their substrate. Now, the lower the Km is, the higher the affinity that an enzyme has for its substrate. So let's say that enzyme A has a Km of 0.001. And the units for Km are going to be something like millimolar. Now, with enzyme A, with a Km of 0.001, that means that you need to give enzyme A this very small amount of the substrate in order to reach half of its maximum velocity. Now, enzyme B, let's say that it has a Km of 1.5. What we're going to do is come up with a ratio or calculate Kcat over Km. And when we do that, we'll see that Kcat over Km for enzyme A, 1 divided by 0.001. That has Kcat Km equals 1,000. So then what we want to do is Kcat over Km equals, well, 6 divided by 1.5 is 4. Now, when we're comparing these two numbers, well, enzyme A, the active sites, the Kcat, might not be quite as extreme or as awesome or as dramatic as enzyme B, but it takes a lot more of the substrate to be present in order for enzyme B to actually do its job. So by enzyme B having a higher Km and therefore a lower affinity, enzyme B is less efficient. So, if we compare and contrast, well, we arrived that enzyme B was better because of the Kcat. But that's only part of the story. We had to get down to, well, how efficient are they? Well, when we do that calculation, Kcat over Km, we can see that enzyme A arguably is a better enzyme for the job. Okay. So now what I want to do, these are like I would argue your most important kinetic parameters, Vmax, Km, Kcat, and then that Kcat over Km ratio. In almost all of these cases, except for the Km, you want the value to be high, or you're kind of anticipating the value is going to be high. A high Km means that the enzyme doesn't really have an affinity or doesn't have a very favorable affinity for the substrate. The lower the Km is, the greater the affinity that the enzyme has for the substrate. Now, when we look at curves for a enzyme, we look at a Michaelis-Menten curve. Michaelis-Menten curve looks a little bit like this typically. And it allows you to make an approximation of the Vmax. And it allows you to say, all right, well, what's approximately the Km? What's the affinity that the enzyme has for the Km? And in order to do that, you take your y-axis and you divide it in two, because your y-axis in a Michaelis-Menten curve is initial velocity. So you cut that in two, here we are. Then we find the coordinates where that halfway point on our velocity aligns with a concentration, which is our x-axis. So our substrate concentration. So let's say that this is 2.5 millimolar. So this enzyme has a Km of 2.5 millimolar. Now, that's what a Michaelis-Menten curve can show you. More times than not, what you want to see is a Lineweaver-Burke plot. And a Lineweaver-Burke plot is pretty commonly used for studies of inhibitors. So here what we've got is no inhibitor. And you might see a question that gives you X and Y values. Let's say that this right here is negative 2.5. This right here is positive 1. Or yeah, say it's 1.5. These intercepts are valuable because these intercepts can be used to calculate your Vmax and your Km. So your y-intercept, which in this case is 1.5, that is a reciprocal value because our y-axis is 1 over velocity, initial velocity, and our x-axis is 1 over substrate concentration. So our 1 over, sorry, this was the label of my axis, 1 over v sub 0. My y-intercept, which in this case is equal to 1.5, is equal to 1 over Vmax. I can solve for Vmax, which I'm doing over here, and I'm going to say 1 divided by 1.5, 1 divided by 1.5 is 0.67. Okay, so this right here is my maximum velocity for this enzyme. Now, my affinity or my Km, that can be calculated by taking my x-intercept, which you have to anticipate will be a negative value. That x-intercept, and you want, since it is a negative value, you want to keep track of it. Say negative 2.5 is equal to negative 1 over Km. These negatives will cancel out, so I'm going to erase them right here, right here. And I'm going to say, and sorry, I'm going to solve for Km by doing the algebra and saying 1 over 2.5, and I get 0.4 millimolar, just as an example. Oh, and Vmax, I'm going to say that that is micromole per second. Okay. Now, the last thing that I want to do with this is clear up, just jump ahead. That helped a lot, I guess. Okay. I'm happy to hear that. Okay. So, and I am recording this and I will post this and share this with everyone later today. So here is my no inhibitor. I'm going to use a couple of different colors here to display what different inhibitors will do. And if you see a line that is parallel to your line of no inhibitor, that means I'm going to say plus inhibitor. I think that it's helpful to look at the axes and say what changed about our axes. Well, did our y-intercept change? It did. Did our x-intercept change? It did. Both of those values changed. Now, what I think is very helpful is to, rather than get wrapped up in, okay, well, how did this inhibitor impact our Km or our Vmax? I plug numbers in and I say, okay, this is 1, this is 3. Okay, so in the presence of this type of inhibitor, my Vmax was 1. And then, because 1 equals 1 over Vmax, Vmax is 1. That's what I would be solving for. Now it's 1 over 3, so my Vmax is gone from 1 to 0.33. My intercept increased, but that's a reciprocal value. So my Vmax went down. Over here, my Km. What happens here? And my Km is negative 2, and now it's negative 5. Is negative 5 a smaller value than negative 2? It is. But remember, those negatives are effectively going to cancel out. So the value of the axis or the intercept increased, but the reciprocal value is going to decrease. So my Km here is 5, or sorry, 1 divided by 2, yeah, it'd be 5. And then my Km here, 1 divided by 5 is going to be, sorry, zero point 0.5, Joel, zero point 0.5. Um, this is going to be 0.2. Okay, now that's what's happening there. What I think is also valuable to know and recognize is, well, what does the line look like? And what type of inhibition is this? With this type of inhibitor, where we have both, we have a change, sorry, when we see a parallel line, if an inhibitor is present and we see a parallel line, this is an uncompetitive inhibitor. Now, another example, or another type of inhibitor, and I'm going to change colors from this. Another type of inhibitor we'll see just a second. Sorry about that. Okay, so another way that an inhibitor can be displayed and what it will impact is if we have, Joel, if our inhibitor and our y-intercept does not change. So I'm going to say plus inhibitor. This is what is known as a competitive inhibitor. My first question with this is, does your Vmax change? Nope, because our y-intercept did not change. Did our Km change? It did. Now, if you have the context of having done this graph right here, well, then you can say, okay, well, my uncompetitive caused my Km to go down, and that means it moved further away from the origin. My competitive inhibitor moved closer to the origin, closer to my 0, 0 origin point. Well, I think that means that my Km increased. Okay. Now, the next thing, so that's a display of two of your types of inhibitors. The other type of inhibitor is the one that throws people for a loop. And one of the reasons is that it's referred to as mixed or non-competitive. I always like to think about this as a process where I say a competitive inhibitor, uncompetitive inhibitors. Those two things are like I've got those etched in my brain on what they do. A mixed or a non-competitive inhibitor is going to be a little bit crazy, in part because they will do different things in the sense of how they will or what their intercepts will be. So now I'm going to go to blue. And the blue line here, I'm going to draw starting from the same point as my no inhibitor present. This blue line, well, what do we know about it? The x-intercept is the exact same. So that means the Km is the exact same. This is synonymous with a non-competitive inhibitor. Okay. Now, did my Vmax change? It did. It absolutely did. Then my last one, I'm going to switch to purple. My purple line, that was just a coincidence. Let me try that again. Okay, I'm going to stop right there. Now, what I want you to recognize about this is that this purple line intersects with my no inhibitor line. Done. I want you to be kind of focused just on the purple and the no inhibitor. This is a purely mixed inhibitor. What has changed? from a mixed inhibitor and no inhibitor, well, the Km has changed and the Vmax has changed. When it comes to does the value go up or down, what I would strongly recommend doing is making sure that I know the graphs, know the curves, know where everything is. And based on that, say, I can plug a number in and figure it out. I personally, I always found it easier and better to know what the graphs do, know what the slope, or know what the lines, know how the graphs look over saying like, oh, well, I know this happens here. Because what I'm going to do is I'm going to use my red pen to indicate my my Km in the absence of inhibitor. So no inhibitor, Km, and I'm going to say that's negative, or no inhibitor x-intercept is -3. Okay. Then over here, I'm going to do the same thing. No inhibitor y-intercept is 0.8. I can follow and I understand what these graphs look like. I understand that these are reciprocal values. And I'm just going to say, all right, well, this goes up, this goes down. What's my new value? I know that right here. If I were to assign a value for that intercept, it's going to be greater than 0.8. So I'm going to say 1.2. And based on that 1.2, that's what I'm going to use to calculate my Vmax. Because I know that 1.2 on a double reciprocal plot will be 1 over Vmax. And then I'm just going to fill this in over here, substrate concentration. And that is where I'm going to stop. I'm looking, if you weren't in my class, I hope you do well on your final. If you are in my class, I hope you do well on my final or on the final. Um, I'll do my best to answer some questions over the course of the weekend, but if anyone has anything, just let me know. Thank you very much. Thank you guys very much for coming. Just let me know if anything comes up. I'll probably be sending an announcement later today about like details of the final and everything like that, and accommodations that I can make. All right, I'm going to stop my recording. No, I just stopped my share, but now I'm going to stop my recording.